Imagine a world where wildfires rage unchecked, floods devastate cities overnight, and our infrastructure crumbles under the strain of environmental crises, yet we have the tools to predict and prevent much of it. That's the thrilling edge we're exploring in the latest insights from NASA's SARP West 2025 Land Group. This group, spearheaded by dedicated faculty advisors Daniel Souza from San Diego State University, brings together cutting-edge research from graduate mentors Megan Ward-Baronier and Robert Purvis to tackle pressing ecological challenges. Their work shines a light on how innovative technologies can safeguard our planet's fragile systems. And this is the part most people miss: these aren't just academic exercises, they're real-world solutions powered by remote sensing that could reshape how we handle disasters. Let's dive into the fascinating world of lichens, those unassuming partnerships between fungi and algae that blanket landscapes worldwide in endless forms. On the west coast of North America, the sturdy Ramalina menziesii stands out with its net-like shape, thriving in three unique environments. In California's coastal Mediterranean climate, this lichen endures with as little as 13% water in its thallus, turning it into a surprisingly potent carrier for wildfire spread. As a species that emerges late in ecological succession, it's been hit hard by rising wildfire frequencies in the area, leading to declines in its coverage. Yet, despite their critical role in ecosystems, studies on spotting these lichens via imaging spectroscopy, which analyzes light reflected from surfaces, are scarce, offering fresh data that could arm wildland firefighters with unprecedented insights. These lichens mostly cling to the region's oaks, with coverage ranging from hardly any to completely enveloping the tree canopies thanks to their dangling growth. This trait makes Art menziesii an ideal subject for airborne imaging spectroscopy. Researchers gathered reflectance spectra using a field spectrometer and contact probe at Santa Barbara County's Sedgwick Reserve's Figueroa Creek site, building a spectral library of 70 samples. This library included three key end members: leaves from Quercus lobata, California valley oak, as green vegetation, GV, with 34 samples, its bark as non-photosynthetic vegetation, NPV, 8 samples, and the lichen itself, 28 samples. They split the library into a simulation set of 41 and an unmixing set of 29 using stratification, then simulated 1,344 mixed pixels with lichen coverage increasing in 5% steps, alongside random GV and NPV portions. Applying multiple end-member spectral mixture analysis, MESMA, to these simulated pixels accurately retrieved lichen fractions with a root mean square error of 0.25 and an R-squared of 0.38, though it sometimes overestimated coverage at high GV levels. Looking ahead, the team plans to test this model using airborne visible and infrared imaging spectroscopy, AVIRIS, data over Sedgwick Reserve. But here's where it gets controversial. Are we underestimating the power of nature's overlooked allies in firefighting, or is technology like spectroscopy just another layer of bureaucracy delaying action? What if prioritizing high-tech detection means sidelining traditional ecological knowledge? What do you think? Shifting gears, Kyra Shimbo from the University of Rochester reminds us that wildfires aren't just flames, they threaten air and water purity, plant life, soil vitality, and human lives. With fires growing more intense, widespread, and frequent, the call for smarter mitigation strategies echoes louder. In 2024 alone, California saw 8,110 blazes scorch over 1 million acres and raze more than 1,800 buildings. Predictive modeling of burn severity in vulnerable zones can guide fire management decisions to minimize risks. Past research has shown that pre-fire elements like fuels and terrain can predict burn patterns, but pinpointing the top influencers and forecasting accurately across varied terrains remains tough. To deepen our grasp of burn severity, they assessed how pre-fire fuels and topography affect post-fire char fractional cover, a stand-in for burn intensity, for the 2024 Lake Fire in Santa Barbara County. Employing a random forest regression model, they predicted char cover using pre-fire data on fuel structure, moisture, condition, water stress, and topography. Fuel structure came from the land, vegetation, and ice sensor, LVIS, a full waveform LIDAR, moisture, condition, and char cover from Earth surface mineral dust source investigation, emit, surface reflectance, water stress variables from the ecosystem spaceborne thermal radiometer experiment on Space Station, ecostras, and topography from the Shuttle Radar Topography Mission, SRTM. Initial outcomes show the model accounts for 28% of burn severity variance, R² equals 0.28, with canopy height, green vegetation fractional cover, and aspect as top predictors. Upcoming efforts could refine this by adding weather data from before and during fires. This tool could monitor fuels tied to severe burns that endanger ecosystems and water supplies. And this is the part most people miss. In an era of climate denial, how controversial is it to invest in predictive models when some argue prevention funds could be better spent elsewhere? Could over-reliance on tech blind us to human-induced causes of wildfires? Share your views in the comments. Nimari Mahajan from the University of Miami explores evapotranspiration, ET, the process where water evaporates from land and plants, crucial for water and energy cycles in dry regions. For years, ET models have relied on spectral indices like the Normalized Difference Vegetation Index, NDVI, to gauge green plant abundance. But NDVI has flaws in semi-arid spots. It flatlines for thick vegetation and picks up soil signals in sparse areas. They investigate if vegetation fraction, VF, from spectral mixture analysis, SMA, of imaging spectroscopy data could offer a better NDVI alternative for ET modeling. Focusing east of Fresno, California, they use data from National Ecological Observatory Network, NEON, flux towers, SJER and SOAP, for ground-based latent heat flux, LE, measurements. VF derives from emit surface reflectance, contrasted with Landsat NDVI in NASA's Priestler-Taylor Jet Propulsion Laboratory, PTJPL, model. Land surface temperature, LST, from ecostras serves as thermal input. Both setups use identical environmental variables, varying only in vegetation cover representation. Early results show SMA-derived VF yields lower LE estimates, especially in patchy or mixed greenery, aligning more closely with tower data, suggesting NDVI overestimates ET here. Though both metrics correlate spatially, R equals 0.73, detailed LE variations underscore SMA's value for subpixel vegetation in ET models. As imaging spectrometers proliferate, this could bolster water tracking, drought-proof farming, and wildfire risk evaluations. But here's where it gets controversial. Is trading NDVI for SMA a game-changer, or does it complicate things unnecessarily for resource-scarce regions? What if embracing new tech means leaving behind tried-and-true methods? Do the benefits outweigh the costs? We'd love to hear your take. Patricia Cibulo at the University of San Francisco tackles urban flooding, a threat to safety, buildings, and urban design. Detecting floods during storms is tricky with persistent clouds blocking views. Synthetic aperture radar, SAR, sensors, like Airborne Uninhabited Aerial Vehicle Synthetic Aperture Radar, WAVSA, send microwaves that work day or night, piercing clouds, and detect water via its high dielectric properties and flat surfaces. With resources, Airborne SAR can track hourly flood changes. Their study applies daily airborne SAR to enhance urban flood mapping, using quad-polarized L-band WAVSA data from 5 days during 2018's Hurricane Florence in North Carolina, plus state flood models. From daily maps, they calculated flooded areas in the northeast Cape Fear River Basin between Wilmington and Goldsboro, measuring overlap with projected 100-year zones. A LIDAR-derived digital terrain model, DTM, at 3-foot resolution highlighted low-lying zones. Findings reveal about 66% of SAR-detected floods outside state models. Future steps might compare WAVSA with less frequent spaceborne SAR, 6 to 12 days, for global mapping. This supports blending high-resolution airborne and satellite SAR for urban flood assessments. The NASA ISRO SAR, NISA, mission, offering global coverage twice every 12 days, could strengthen this. Pairing SAR with LIDAR promises faster, accurate disaster responses. And this is the part most people miss. In flood-prone cities, is high-tech SAR the hero we need, or does it distract from fixing outdated infrastructure? Could prioritizing satellite tech overlook community-based flood prep? What are your thoughts on balancing innovation with equity? Charlotte Perry from Stonehill College delves into geothermal wonders like mud pots and volcanoes, signaling underground heat and energy potential. California's Salton Trough generates about 340 megawatts of electricity.